The method of Lagrange multipliers can help us find the absolute extrema of a function over some constraint. The function whose max or min we want to find, we usually call f, and that's our objective function. Our constraint we usually call g, and in order for this all to work out, we're going to arrange g in such a way that all of the variables are on one side, and the constraint that they're equal to is just a constant. The things we're finding here are not technically the same as critical points. We think of them as somehow points of interest. We'll find a collection of points, and the absolute max and min will be among those collections of points. And the way we find them is we find the points that satisfy these three equations. The third equation is just the constraint. We're not interested in any points that don't satisfy the constraint. The first two equations really give rise to two cases. It could be the case that our partial derivatives are both zero. That would make this equation true. If they're not both zero and the equation is true, then in particular g sub x is not zero, so I can divide by it. So the first equation always gives us these two cases, and then similarly the second equation gives us these two cases. It could be the case that these partial derivatives are both zero. If it's not, then gy is not zero, so I can divide both sides of the equation by g sub y. Now, depending on the actual functions we're working with, it's often the case that we can immediately rule out at least some of these cases. But if we can't rule them out immediately, this actually gives us four options. And then in each of these four cases, we find which of the points that make that true and in addition satisfy the constraint. Another thing to note is that in cases 2 and 3, we can choose lambda to be whatever we want. So really the thing we're concerned with in case 2 is that these partial derivatives are zero. We don't actually have to find lambda. And so we can just say, well, I make lambda whatever it needs to be to make the second equation true. In scenario 3, we really have to focus on these partial derivatives being true, and then lambda, well, we just make it whatever it needs to be in order to make equation 1 true. In scenario 4, this leads us to equate the two lambdas. The lambda needs to be the same in both equation 1 and equation 2. So scenario 4 can be written like this. Here's a very typical example of a utility function. The thing that we want to take the maximum of, that's our f. Our constraint function, that's our g, and notice it is set equal to a constant. That constant is 0. So let's set up our three equations. F sub x is 4 times x to the minus 3/4 times y to the 3/4. F sub y is 12 x to the 1/4 times y to the negative 1/4. G sub x is 50, and g sub y is 100. Now, it is never the case that g sub x is 0, and it's never the case that g sub y is 0. So the only way for this to be true is if lambda is equal to 4 over 50 times y over x to the 3/4. Similarly, it is never the case that g sub y is equal to 0. So I can definitely divide by g sub y. Lambda must be equal to 12 over 100 times x over y to the 1/4. So in order for both 1 and 2 to be true, it must be the case that this lambda is the same number. The only possible way to have the first two equations true is to have y equals to 3/2 x. Now we build in our constraint. We are only concerned of values of x and y, where 50x plus 100y is 500,000. By considering the constraint, we find that x needs to be 2,500. We also still know the relationship of x to y. Y has to be 3/2 x. We're asked for the maximum value of the utility function. So we want to find what u is when x is 2,500 and y is 3/2 x. This will be 16 times 2,500 to the quarter times 3 times 2,500 over 2 to the 3/4. Now there's some fine print here. It says you don't need to justify your answer, but you do need to use the method of Lagrange multipliers. So you need to do all the steps we just did. That's the method of Lagrange multipliers. What we don't need to justify is that this is a maximum. We only found one point of interest, so we can trust that it's a maximum. To find the minimum, I would look here at these constraints when x is 0 or y is 0. Those would give me the minimum value of my utility function, which would be 0. The objective function is what we want to find the max and min of. The constraint function is our constraint. In this case, that's x squared plus 2y squared, and it needs to be equal to the constant 4. So we start by setting up our equations. The third one is just our constraint. F sub x is minus 8x, and f sub y is 2y. G sub x is 2x, and g sub y is 4y. In equation 1, it could be the case that 2x is equal to 0. In that case, I would also need negative 8x to be equal to 0. So it could be the case that x is equal to 0. That would make my first equation true for any lambda in the world. If 2x is not 0, then I can divide both sides of the equation by it, and lambda needs to be negative 4. So in order for equation 1 to be true, at least one of these two things needs to happen. Now let's look at equation 2. It could be the case that 4y is equal to 0. If 4y is equal to 0 and this equation is true, then the left-hand side of this equation is true as well. So if y is equal to 0, then this equation is true for any lambda. Or, if 4y is not 0, I can divide both sides of the equation by it, and I find that lambda is 1/2. Now let's go through and think about our scenarios. If x is equal to 0, then the first equation is true. In order for the second equation to be true, it could be the case that y equals 0, or it could be the case that lambda is 1/2. If x is not equal to 0, then lambda must be minus 4. That makes the first equation true. Then if y equals 0, that makes the second equation true. If I try and let lambda be 1/2, this is not allowed. My lambdas have to be the same, so this fourth scenario doesn't happen. Now we test these against our constraint. If x is 0 and y is 0, then our constraint does not hold. So we are not interested in this point. Suppose x is 0. Then my constraint tells me that y is plus or minus the square root of 2. So this gives me 2 points to consider. X is 0, and y is the positive or negative square root of 2. Finally, what do we do if y is equal to 0? Let's look at our constraint. This tells me x is plus or minus 2, so the points to consider we get out of this are when x is positive or negative 2 and y is 0. So there are 4 points we need to consider. I know that my absolute maximum and minimum of f of x subject to the constraint will occur at a point that makes those 3 equations true. That means the max and min will occur at one of these 4 points. So now we just plug these into our objective function and see what we get. The biggest of these values is 2, so that's the maximum. The smallest of these values is minus 16, so that's the minimum. In part A of this example, our constraint function is x squared plus y squared is equal to 4. So g we can write as x squared plus y squared. Let's set up our first two equations. F sub x is 2 times x minus 1. F sub y is 2 times y plus 1. G sub x is 2x, and g sub y is 2y. So it could be the case that g sub x and f sub x are both 0, or it could be the case that lambda is 2 times x minus 1 divided by 2 times x. Now notice this first one doesn't happen. If 2x is 0, then 2x minus 1 isn't 0, so we don't actually have to worry about this one. The second equation proceeds the same. If g sub x is 0, then for this equation to be true, f sub x has to be 0 as well, but those can't both be 0. So it must be the case that lambda is 2 times y plus 1 divided by 2y. So in order for both 1 and 2 to be true, it must be the case that x minus 1 over x is the same as y plus 1 over y, because lambda has to be the same in both of these two functions. This tells us x times y minus y is equal to x times y plus x. So y is equal to negative x. If y is equal to negative x, we can make the first two functions true by setting lambda to be this number, which will be the same as that number. Now we need to make sure that our third equation is true, our constraint. If y is equal to negative x, this simplifies to 2x squared is equal to 4. So x is plus or minus the square root of 2. So the points we get to consider are when x is the square root of 2 and y is negative x, and when x is the negative square root of 2 and y is negative x. I know the max and min of my function over this constrained curve will be at one of these two places, so I plug them into my curve. When x is the square root of 2 and y is the negative square root of 2, the value I get is this. Since these terms are both squared, it doesn't matter whether I have the positive version or the negative version. After I square them, they're the same. Now it's easy to see that root 2 plus 1 is bigger than root 2 minus 1. So this number is the maximum of my function over its constraint. This number is the minimum. There's a part B to this question, and the part B asks us about a region with both a boundary and an interior. The region in question is just a circle of radius 2, centered at the origin. And we have already found the max and min along the boundary. Along the boundary, part A has already told me what the max and mins are. Here at positive root 2, negative root 2, this is my min. Here at negative root 2, positive root 2, this is my max. In order to find the max and min over the entire function, we need to check and see whether there's any critical points on the interior of my region. To check for critical points, I want to know where my partial derivatives are 0. I need both of these to be 0, so the only critical point is when x is 1 and y is -1. That is inside my region. Let's figure out what the value of the function is at this point. The value of the function here is 0, and that's smaller than either of my two boundary extrema, so that is the absolute extrema over the entire region. It didn't come up in part A because it doesn't exist on the boundary. In part B, I'm considering a bigger region. So on the region R, the maximum value of our function is 2 times root 2 plus 1 squared, and the minimum value of our function is 0. Our objective function is the thing we want to find the max and min of. We're asked to find the max and min of this function, so this is our f. Our constraint function is this circle, so x squared plus y squared is our g. Let's set up our standard two equations. The partial derivative of f with respect to x is 2 times x plus 1. The partial derivative of g with respect to x is 2x. The partial derivative of f with respect to y is 2 times y minus 2, and the partial derivative of g with respect to y is 2 times y. From the first equation, it could be the case that 2x is equal to 0. In that case, 2 times x plus 1 would also have to be equal to 0, and I see that this can't happen. If that's not the case, then I can divide both sides by 2x, and lambda will have to be x plus 1 divided by x. The second equation is similar. If 2 times y is equal to 0, then 2 times y minus 2 must also be equal to 0, and those two things can't be true at the same time. So it must be the case that 2 times y is not 0, and if it's not 0, I can divide by it. So the only way to make the first two equations true is if lambda can be written as x plus 1 over x, and can also be written as y minus 2 over y. That tells us xy plus y is equal to xy minus 2x, so y is minus 2x. If y is equal to negative 2x, then this expression and that expression give me the same number, and that's important because I need lambda to be the same number in these two equations. The third equation is my constraint. I only care about x's and y's that are on the circle. X squared plus y squared is 125. If y is negative 2x, that tells me x squared plus 4x squared is 125. So 5x squared is 125. X squared is 25. X is positive or negative 5. So that gives me 2 points to consider. If x is 5, y is minus 2 times x, so y should be negative 10. If x is negative 5, y should be positive 10. These are the only 2 points that make all 3 of these equations true, so the max and the min will be among these 2 points. To figure out which is which, we plug them into our function. The maximum value of our function is 180. The minimum value of our function over our constraint is 80. That finishes part A. Part B is closely related to part A. We want to consider points on a circle that are close to the point negative 1, 2. So this is the circle of radius root 125. Here's the point negative 1, 2. And I want to find what point on the circle is closest to it. So the distance from the point minus 1, 2 to the point xy is the square root of x minus negative 1 squared plus y minus positive 2 squared. And notice this is the square root of our objective function from part A. So whatever makes the inside of this square root smallest makes this whole function smallest. So we already found that this is minimized by the point negative 5, 10. So this is the point that is closest to the point negative 1, 2 on the circle of radius root 125. Our objective function in this problem is this cubic function. Our constraint function is x squared plus y squared, and the constraint is that it needs to be equal to 4. So this is g. Let's start with our usual first two equations. F sub x is negative 6 times x times y. G sub x is 2x. F sub y is 6 minus 3y squared minus 3x squared. G sub y is 2 times y. For the first equation, it could be the case that 2x is equal to 0. In that case, negative 6xy would also have to be equal to 0. And this is true if x is equal to 0. So if x is equal to 0, our first equation is already true. If x is not equal to 0, then I can divide by it. And then lambda is minus 6x times y divided by 2x, which is minus 3y. Again, this is the case that x is not equal to 0, so it makes sense to divide by it and it makes sense to cancel. For the second equation, it could be the case that 2y is equal to 0. If that's the case, then in order for this to be true, I also need the left-hand side to be equal to 0. So 6 minus 3y squared minus 3x squared would have to be 0 as well. This first part of the equation tells me y is equal to 0. Coupling that with the second part of the equation tells me that 6 is equal to 3x squared. So x is plus or minus root 2. That's one way to make the second equation true. If 2y is not equal to 0, we can divide by it. Let's consider the 4 ways of combining these. I can't have these two be true at the same time, because this one makes x equal to 0, and this one makes x equal to plus or minus root 2. So that one's not on the books. If x is equal to 0, then it must be the case that lambda is equal to 6 minus 3y squared minus 3x squared over 2y. So this is one possibility. If x is not equal to 0, then lambda is equal to minus 3y. It could be the case that y is equal to 0 and x is equal to plus or minus root 2. Or it could be the case that lambda is equal to 6 minus 3y squared minus 3x squared over 2y. So here are my 3 remaining possibilities, again, because we can immediately rule out the possibility that these two things happen. They can't happen at the same time. The thing to do next is to check all of these against the constraint, but I want to remind you sort of what's important and what's not. In this scenario, if x is equal to 0, then equation 1 is satisfied no matter what lambda is, so I don't actually have to work with this, because I just make lambda whatever lambda needs to be. That makes equation 2 true, x equals 0 makes equation 1 true, and I'm done. So I don't need to work with that value of lambda. The same is true in this scenario. If I make y equal to 0 and x equal to plus or minus 2, then that satisfies the second equation no matter what lambda is. So then I just choose lambda to be 3 times y, whatever y is. That makes the first equation true as well. So again, I never actually have to use that lambda is minus 3y here. So here are the 3 scenarios that I need to consider. The one on the right is the easiest to think about my constraint. I need x squared plus y squared to be 4. But in this case, it's just 2. So my constraint is not satisfied, so I don't care about this point. And now I'm down to considering just 2 scenarios. In the scenario that x is equal to 0, I plug this into my constraint. And I get that y is equal to plus or minus 2. So the points I get to consider are 0 and plus or minus 2.
Our final case to consider involves these two values of lambda. We need to find x's and y's that make these two expressions the same, because lambda has to be the same in equation 1 and equation 2. And they also have to satisfy the constraint. Since we're going to be plugging something into the constraint, it's nice to solve for x squared or for y squared. Let's start by multiplying both sides of this equation by 2 times y. We could go ahead and solve for x, but for the purposes of plugging this into our constraint, it's actually easiest to leave this as x squared, because our constraint is x squared plus y squared. Now that I've found y, I can find the x's that go with it, and those will be my points to consider. So I get 4 points to consider. X is the positive or negative square root of 3, and y is positive or negative 1. These 6 points are the only points that make my system of 3 equations true, so the absolute max and absolute min will be among these 6 points. Although I have 6 points to consider, if I'm clever, I can get away with only considering 4. Because x shows up squared and only squared, positive and negative values of x will give me the same function value. So I can combine points to consider if the only difference between them is the sign of x. I can't do the same with the sign of y. Since y is raised to all odd powers, the sign of y will impact the sign of my function. The largest of these is 4, the smallest is negative 4, so the maximum and minimum values attained by f on the circle described by G are 4 and negative 4.